Hello, all attendees. I would like to welcome you to this RVfpga webinar hosted by Digi-Key and sponsored by Imagination Technologies. We're honored to have today Professor Sarah Harris from UNLV joining us. Professor Harris is an FPGA expert and also an expert in the risc-v processor architecture. She'll be presenting and also demoing the implementation of a risc-v core inside a Xilinx FPGA running on a commonly available Digilent board that's designed for the classroom. And if you do see Professor Harris's board today, if she pans her camera down, it will be mounted on a face dock. Face dock is a mounting solution for electronic project boards, and in a way that's really smart, and it will basically protect the project from sliding around and being messed up, from being carried from one room to another or one workstation to another. So without further ado, Professor Harris, the stage is yours. Thank you.
Thank you, YC. It's great to be here. As YC said, my name is Professor Sarah Harris. I'm a professor at the University of Nevada, Las Vegas. And I earned my PhD from Stanford now many years ago in electrical engineering. I'd like to also acknowledge all of our contributors and associates and industry sponsors and supporters, and especially my co-author, Danny Chavert, and the Imagination University program, which has driven the RVfpga program. And Robert Owen is the director of the Imagination University program. So today we're going to talk about what is RVfpga, so an introduction and then an overview of what this course and the system is. And then I'll give a brief demonstration, about a 7-minute demonstration of how to use the system. And then I'll give a sampler of some of the labs that we include in our course. So what is RVfpga? RVfpga stands for risc-v FPGA. So it's a course that shows how to target a swerve commercial risc-v core and system on chip to an FPGA. And so we show how to program the risc-v SoC onto the FPGA and then also run programs on it and extend the SoC itself to add functionality. And we also show how to analyze and modify the risc-v core itself and the memory hierarchy. So as I said, this package is being developed by Imagination Technologies, and particularly the Imagination Technologies University program and its academic and industry partners. And after completing this course, this RVfpga course, users will walk away with not only a commercial risc-v core and SoC and ecosystem, but they can also both use and modify it. And so I also wanted to point out a second course, which I won't go into detail today during this webinar, but it's called the RVfpga SoC course. And it's a second course that shows how to build a risc-v SoC from scratch. So from using the processor and the peripherals and the memory and putting it all together into an SoC. And this also shows how to install the Zephyr real-time operating system and then run programs on it, including simple TensorFlow programs. And that course has 5 labs. Both of these courses are available for download, and maybe some of you have already downloaded them from Imagination Technologies, given it the link here. So again, today we're going to focus on the first course, the RVfpga course. And the goal of the webinar is to introduce an overview of this course and demonstrate the system and give a sampler. At the end of this, you can then go and try these out on your own, running the hands-on labs, the getting started guide, and so forth. So let's talk about what's included in the course, in the RVfpga course. So the target audience is basically everyone. So academics, industry professionals, researchers, students, basically anyone interested in risc-v processors. And there's some expected prior knowledge, including digital design, high-level programming, preferably C, assembly program, instruction set architecture, mark architecture, memory systems. And all of this material is covered in Digital Design and Computer Architecture, risc-v edition, that is authored by myself and my co-author, David Harris. This book came out in 2021, just a few months ago in October. So the RVfpga system includes the SWRV EH1 core, which is a commercial open source core from Western Digital, and that is the center of this system. So this core has a two-way superscalar core with a 9-stage pipeline. It's in order and runs the RV32i MC, so the RV32i instruction set with the multiply, divide, and compressed instruction extensions. So around this core is the core complex, which includes some interfaces, and then around that is the SoC, the SWRV-ULF, and we add the X because we extended it. We added a few peripherals, SWRV-ULF system on chip, which is also open source, created by Olaf Kindgren. And then around that, we target it to either the Nexus A7 FPGA board that's shown on the top here, or simulation. And so those two either targeted to the Nexus A7 FPGA board or simulation, that's what we refer to as the RVfpga system, which we also sometimes call just RVfpga. So what's included in the package that you download from Imagination Technologies? And again, that download is free upon registration. Well, there's a getting started guide, which includes a quick start guide, an overview of the risc-v architecture and RVfpga, and it also shows how to install the tools. After doing the getting started guide, you can then move on to the labs. There are 20 labs altogether. Labs 1 through 10 show how to program and extend the RVfpga system by adding peripherals, and then also how to build the RVfpga system from the sources, from the Verilog and System Verilog code that's included in the download. And then labs 11 through 20 really dive into the core itself and the memory system and show how to understand the core and the pipeline and the memory system, and then also extend them. We'll also be creating an edX course in the next few months, so you can look to that as well. So what is the required software and hardware? Well, the hardware is optional, and all of the software is free. So we use Xilinx's Vivado Webpack, which is a free download, and then Platform.io, which is an extension of Visual Studio Code. And within Platform.io, we also use the Chips Alliance platform, which includes the toolchain, Verilator, HDL simulator, and Western Digital's Whisper instruction set simulator. The hardware, again, is optional. The Nexus A7 board, it's also compatible with the Nexus 4 DDR board, which is an older board. And all RVfpga can be run in simulation or hardware, so that's why that part is optional. Of course, you know, we're pretty big fans of hands-on, so the hardware option is a nice option to have. The core and SoC itself, they're both open source, and they're provided by Western Digital, the core, the SWRV EH1 core, and Chips Alliance provides the SWRV-ULF system on chip. Again, you can get those in other ways, but they're included already with the RVfpga system. The operating systems that are supported are Windows, Mac OS, and Ubuntu 20.04. So here's a picture of the Nexus A7 100T FPGA board, and it contains in the center the Artix 7 FPGA, or Field Programmable Gate Array, and then some peripherals, including some that are pointed out in this figure: push buttons, 7-segment displays, LEDs, and switches, and then some additional ones such as accelerometers, temperature sensors, microphones, etc. And you can purchase these at Digi-Key or at Digilent. We will also provide support for smaller boards, including the Basis 3 FPGA board, which is a smaller and less expensive board. All right, so let's move on to the demo of the RVfpga system. So as I said, we can run RVfpga in hardware by targeting it to a Nexus A7 FPGA board and using Platform IO to download that RVfpga system onto the board and then download a program onto that RVfpga system running on that FPGA board. Or we can run it in simulation. And we show how to do that in 3 ways. Verilator, it's an HDL or hardware description language simulator. Whisper, which is Western Digital's instruction set simulator. And VidBo, which is a virtual development board. That last one, VidBo, is in the beta version. So if you downloaded the RVfpga package from Imagination, it won't include that yet, but we wanted to show how that will work. And again, that's in the beta version right now. I also want to point out that Verilator and VidBo are actually simulating the RVfpga system itself. Whisper is an instruction set simulator, so it's simulating just the program on a generic risc-v processor. All right, now we'll go to the demonstration of these ways to run RVfpga.
To run the RVfpga system on the FPGA board, we first run Visual Studio Code. We click on File, Open Folder, and browse to where you've placed the RVfpga folder that you downloaded from Imagination Technology. We click on the example subfolder and click on the LED switches C-Lang folder and click Select Folder. Now we open the platformio.ini file. This is the initialization file for platform.io. And you want to change the location of the bitstream file, which is the definition of the RVfpga system that will be downloaded onto the FPGA, that will configure the FPGA. Change that path. And now we will download the system, the RVfpga system, onto the board. First, we turn the board on by using the switch at the top left of the board of the Nexus A7 FPGA board. And now we click on the Platform.io icon and scroll down under Project Tasks to Upload Bitstream. We can see in the terminal window that it was successful, and now we'll load the program onto it by clicking on Run and Debug in the left ribbon menu, and then click on Debug. Make sure that PIO, Platform.io Debug is selected there. Now we click on Start Debugging. This downloads the program, in this case the LED switches C-Lang program. This is a C program that reads the switches and writes their values onto the LEDs. And so we have control buttons up here, continue, step over, step into, the typical debugging operations. And we can also set breakpoints in our code by clicking on a line, and then we click again to remove that breakpoint. So we click on Continue. We can now see the program running on the Nexus A7 FPGA board. As we toggle the switches, the corresponding LED lights up or turns off if we turn the switch off, because the program is reading the switch values and then writing that value to the LEDs. To run the RVfpga system in Verilator, we first need to build the simulation binary, the simulator binary. So we change to the directory where we've stored RVfpga, the folder downloaded from Imagination Technologies, and then change to the Verilator sim subdirectory. Now we perform the make clean command, followed by the make command. This builds the simulator binary. After we've compiled the simulator binary, we'll go back to VS Code, Platform.io, and select File, Open Folder. This time we'll select the AL operations folder. We open the platformio.ini file and make sure that the location of the simulator binary, the verilator binary, is correct. Now we click on the Platform I/O icon and Project Tasks and scroll down to Generate Trace. Now we run GTK Wave. And we click on File, Open New Tab. We make sure we're in the AL Operations folder and then scroll down to select trace.vcd. Now we can see the hierarchy of the Verilog and System Verilog modules on the left pane here, and we can expand them: RVfpga Sim, Swerve ULF, Swerve EH1, and Swerve. And now we want to click on the instruction fetch unit, the IFU, and we'll grab some signals to look at them, the instruction and the clock. Because it's two-way superscalar, we have a way 0, I0, and a way 1, I1. And we can use the zoom buttons to look at our waveform. Now we can view the instructions that are fetched in each of the ways, and we can, if we look at the AL operations code, we can see that in fact this is the machine code for the instructions in the repeated loop inside that code. To use the Whisper instruction set simulator, we go back to Platform I/O and we uncomment the debug tool equals Whisper line in platform io.ini. Now when we run and debug the program, it will run in software using this instruction set simulator instead of in hardware on the FPGA board. We click on Start Debugging. And this interface looks the same, but now we're running it in simulation. To run the RVfpga system using VidBo, the virtual development board, we open terminals to load the program and to run the server that will show us the board using the web interface. In a Windows machine, we need to do this inside of a virtual machine using VMware. So here we have one terminal window where we've changed to the RVfpga verilator sim_vidbo directory, and we load the program onto it. In this case called firmware_LED switches -hello world.vh. A second terminal runs the server, and then we open up a web browser and connect it to localhost :8000 and click on nexus-a7.html. And now we see a picture of the board show up, and this is a virtual board. And so after we connect to board, click on connect to board, it is now running the program so we can toggle the switches, and it is as if we're running it on the hardware itself. But instead we're running on this virtual board called VidBo.
So now we'll talk about an overview of the labs. And I want to, before we move on to talk about the labs, I want to just mention how, within 7 or 8 minutes there, you can see how we can run the RVfpga system and really get hands-on experience with the risc-v core, pretty readily. And so one wonderful thing about this course is that it makes the risc-v architecture accessible and really usable pretty quickly. So the labs that we've developed are in 2 parts. Part 1, labs 1 through 10, talk about programming and building a Vivado project to synthesize the core and SoC and target it to an FPGA. And we also talk about peripherals, I/O systems, and how to extend the RVfpga system to include other peripherals. In part 2, we focus on the risc-v core and memory systems, as well as benchmarking and performance monitoring. And all of these labs include not only examples and kind of tutorials, but also exercises for using and or modifying the RVfpga system to increase understanding through hands-on design, and also to extend the functionality of the RVfpga system. So these also include solutions in assembly and in C. So here's a detailed list of the Part 1 labs and the Part 2 labs. I'm going to talk about each of these parts in the next slides. So Part 1, again, shows how to program the RVfpga system. So labs 1 through 4 show how to program in C first, and then risc-v assembly in labs 1 and 2. And then talks about function calls and the risc-v calling convention. And lab 4 shows how to combine C and assembly programming using an image processing application. And then lab 5 is kind of the glue between the two halves of peripherals and programming. It shows how to create a Vivado project using Xilinx's Vivado a tool. And so you're going to need to do that because in the next labs, we're going to be modifying the RVfpga system, extending its functionality, and then using Vivado to synthesize the now modified RVfpga system. So the next labs 6 through 10, first give an introduction to the I/O systems, to peripherals, talk about the 7-segment displays and some timers. These are some kind of typical peripherals that we often use. And lab 9 talks about interrupts, and lab 10 talks about serial buses. Part 2, the second half of the labs 11 through 20, again, dive into the core and focus on the pipeline, performance monitoring, and extending features inside the core itself and the memory system. So lab 11 talks about how to configure the Swerve EH1 core, so it is configurable, and how to use the performance monitoring, so the hardware counters and so forth. Labs 12 through 16 dive into the pipeline and show how different instructions flow through the pipeline, which modules and which signals indicate which instruction is flowing through the pipeline and so forth. So lab 12 focuses on the add instruction, lab 13 loads and stores, lab 14 through 16 hazards, structural data and control hazards. And then we really focus on superscalar, the superscalar features in lab 17, and lab 18 talks about adding features, including floating point instructions and counters. Lab 19 talks about the instruction cache, and lab 20 talks about on-chip memories and then benchmarking, which we can use then to, once we modify the system, to measure, well, how did that affect performance? So now I'm going to give a sampler overview of some of these labs. And again, after this webinar, the fun part is that you can then dive in and try these hands-on using the RVfpga package. So we'll talk about a few of the labs from the entire package. Lab 1 is C programming. And so we show how to so in the demonstration, we showed how to use an existing project, but in this lab, we show how to create a project in Platform IO, then write a C program and run and debug the program using either hardware, the Nexus A7 FPGA board as a target, or one of the simulators, right? You can run it in one or all of those ways. And so one thing we talk about is memory mapped IO addresses. In our system, in the RVfpga system, switches are mapped to the address given here, hex 8000-1400, and they're mapped to the upper 16 bits. So we can read the switch values by reading from that address. And the LEDs are mapped to the lower 16 bits of hex 8000-1404. And then we have a way of setting the pins, the general purpose IO or GPIO pins, as inputs or outputs by either making the bits in this register, and this is mapped to this memory location as ones outputs or zeros inputs. And so we can see this in this example program that we include in Lab 1, where we basically set the upper 16 bits as inputs, that int enable value equals hex FFFF. See if I can. So that line right there shows how to enable the either driving them as inputs or reading them as outputs. And then the next few lines show how to read from those values, read those registers, and then display the values on the switches. So the last line here displays the values from the switches onto the LEDs. And so another feature that we show how to use is Western Digital's BSP and PSP, the platform support package and board support packages. And these provide common functions. For example, the printf nexus, which is like printf in C, just allows us to see that output on using platform I/O. And so here's an example of using the UART inside RVfpga to print to the terminal. And again, the terminal is within platform I/O. And so we include the PSP API and then initialize the UART and then print just like we would print in other C programs, but now we use printf nexus. And so we include this line in our platformio.ini file to set the speed of the UART. And then in platform I/O, we open a terminal so we can view that output. Lab 2 is very similar to Lab 1, but now we're using risc-v assembly instead of C. And so the steps are essentially the same, except step 2, which is to write an assembly program instead of a C program. So here's a listing of some of the most common risc-v assembly and instructions and pseudo instructions that we demonstrate and use in this lab. And here is some additional instructions. And we use the 32-bit registers from risc-v shown here. And again, they have numbers here in that column, register numbers. And they also have names that, by convention, we use them for different purposes. For example, X1, register 1 is used as the return address for calling functions. And so here is the same program that we just saw for C, but now written in assembly. And so we can see it's reading the switches, for example, shifting those switches, that value to the right, because remember the switches are in the upper 16 bits of that register. So we shift them down and then write the value of the switches to the LEDs. And again, we use those memory mapped I/O addresses that we've mapped to those general purpose I/O. And these are all provided in the RVfpga package. This is the path where you've placed your folder once you've downloaded it, and then the subfolders there. In Lab 6, we start talking about peripherals or input-output devices. And so a common input-output device is general purpose I/O, GPIO, and we include a GPIO controller. And so these next labs 6 through 8, show how to first understand peripherals and then extend to other peripherals. And they include 2 types of exercises. The first one is programs that actually exercise those peripherals. And the second one is writing HDL code to extend the RVfpga system to add another peripheral. For example, in Lab 6, we have exercises to add support for the push buttons via a new GPIO controller. Lab 7 shows how to modify a 7-segment display. one of the exercises. And then Lab 8 adds support for a tricolor LED and shows how to use them with pulse width modulation. So here's the overall structure of the peripheral interface. So we have the SORV EH1 core here. It has an AXI bus. And so we use an AXI, a wishbone or WB wishbone to AXI bridge because many open source peripherals use a wishbone bridge or wishbone bus. And then we have our multiplexer, which chooses amongst the peripherals. And then we also have our peripherals here shown on the left. And so these peripherals listed here are the ones that are included in the RVfpga system, which includes the boot ROM, system controller, which inside of that is a 7-segment display controller. We have 2 SPI interfaces, one for flash memory and one for the accelerometer, a UART, and then GPIO for the LEDs and switches, and a timer. And so in general, GPIO, general purpose IO, has a kind of block diagram shown here. So we have a read register that gives us the value from the peripheral. So here are peripherals. Here's the example, the LED and the switch. And so we have a read register, and we read from that register to get the value of those pins. And then we may want to write a value. So we have a write register, but we have to have an enable register so we don't have contention on the actual pin itself, on the wire itself. And so we have an enable, a tri-state enable here, and the enable, when we write it to 1, it allows it to be an output. Right here, it enables that register to connect to the wire, the actual wire. And when it's 0, it's an input. So the GPIO module that we use is from OpenCores, and the link is shown here. It allows up to 32 GPIO pins, and all pins can be individually configured as either inputs or outputs. And that configuration can change throughout the program. And here is, again, a review of the memory mapped I/O addresses of those read, write, and enable registers, and code that shows how to read and write those registers. So Lab 7 talks about 7-segment displays, and we start with this because a lot of people have experience with these. And so we have a known peripheral, and even if not, we explain it in the lab. And then we show how to integrate it into the RVfpga system. And so we give an overview of how 7-segment displays work, and then talk about the 7-segment display hardware. So 7-segment displays are everywhere. They light up, one or several, usually several of the segments. For example, the number 1 lights up 2 segments to display the number 1, and other of the segments, these 7 segments A through G, light up to display different numbers. And so we have an 8-digit 7-segment display. So there are 8 7-segment displays on the Nexus A7 FPGA board. And so we have these 2 registers, the enables register that enables whether we're writing to that digit. So we have 8 of those, the lower bits are what we use to enable those registers. And then we have a digits register that says which digit we want to display on those 7-segment displays. So for example, if we want to enable the 2 rightmost digits, we'll make them 0, 0, those enables. So these are low assorted enables. So those 2 rightmost digits, make them 0, 0, and then we write hex 7, 1 to the digits register to have the value that we want to display, the hex 7, 1. And the code for doing that is shown here. So we have our hex FC, which is this value here in hexadecimal. And then we have the digits value put into temporary registers, into T1 and T2, respectively. And then we write those values. So T1, we're going to write to the enables register, so 0 plus that memory address. And then we're going to write the actual digits to the digits register, so T2, which contains hex 71. And just as we saw in the other peripherals, it has 3 parts: the connection to the 7-segment displays, so that physical connection, and that's on the PCB. On the Nexus A7 board, it has traces from the FPGA pins to those 7-segment displays. And then we have the system controller, syscon here, that controls the 7-segment displays, and then the SWIR EH1 bus interface, including the multiplexer and address decoder. That our address decoder detects on which address is being written to or read from to route it to the correct peripheral. In Lab 9, we talked about interrupt-driven I/O. So there are 2 types of really coding: interrupt-driven I/O versus programmed I/O for interfacing with these peripherals. And we use the RVfpga system interrupt controller and show how to configure the interrupts using Western Digital's PSP and BSP. And we give an example of how to do this. So as many of us know, programmed I/O pulls continuously. So that those previous programs were pulling the switches kind of continuously throughout the program and then writing the value to the LEDs. And that can be pretty demanding, and it eats up a lot of time. In fact, in the previous examples, all the time for the program. Instead, we can use what's called interrupt-driven I/O, where we have an interrupt that says, hey, there's a new value on the switches or whatever peripheral we want to interface with. And only then does the processor get interrupted from what it's already doing to then handle that interrupt. And how it handles that, the code that handles that, is called an interrupt service routine, also called an interrupt handler. And so this frees up the processor to do other work while waiting, while in the background waiting for this event to happen, or this interrupt to happen. So this is the programmable interrupt controller, the PIC, that's inside of this SWIR EH1 core complex. And it interfaces with a GPIO, has interrupts and timer. So we show how to use that with 2 different interrupts. The general steps are to first initialize the interrupt system, and then we initialize the external interrupt line. In this case, we use interrupt request 4, IRQ4, and initialize the GPIO registers to use interrupt. So we enable the interrupt for switch 0. Remember, the switches are mapped to the upper 16 bits of that register, and so we put a 1 into bit 16, which is the rightmost switch. And then we say that we want to trigger on the rising edge. So we put a 1 here again in bit 16 of the trigger register. If we wanted it to trigger on the falling edge, we would have put a 0 there. And then we clear all the interrupts and enable GPIO interrupts. And finally, we enable global interrupts. And so I'm going to just show an overview of that code here. Here's the ISR, or the interrupt service routine. And in this case, what we want to do is we want it to change. It can do whatever we want it to do, but in this case, we just invert the LED and make it turn on and off when we get an interrupt. And so we do that here, and then we clear GPIO interrupts and clear that specific interrupt, so it's not continuously interrupting the processor. Right? It'll wait for the next actual interrupt before returning. In Lab 10, we talk about serial buses. And so we have several common serial buses are UARTs, SPI, and I2C. These serial buses, instead of sending a bunch of bits on multiple wires, send a single bit at a time. So this is serial bus versus parallel bus. And the UART, which is included in the RVfpga system, is a universal asynchronous receiver transmitter. SPI stands for serial peripheral interface, and I2C stands for integrated circuit protocol. In this lab, we focus on the SPI interface, but any of those different protocols could be used. And so here's a picture of the SPI interface. We have an SPI controller and then the SPI peripheral. And so the controller, which is the RVfpga SoC, sends the clock and sends and receives data, whereas the peripheral receives the clock from that controller, in this case, the controller is RVfpga, the RVfpga system, and sends and receives data as well. So we have these interface signals. SDO stands for serial data out, and SDI stands for serial data in. S clock stands for SPI clock. And there's another signal, which I haven't mentioned yet, CS bar, which is the chip select signal. And that's if we're sharing wires among multiple peripherals. So only one of the chips or the peripherals will be selected at a given time. So chip select is a low asserted signal. So that's why it's called chip select bar. And so here's an example of the signals. So here's our waveform with time on the x-axis, and these signals, S clock and STI-O, serial data in, serial data out, and STI and STI-O. And so on the rising edge, S clock samples bit 7, bit 6, and each of the bits. And then on the falling edge, the data is sent. That's configurable as well. So we use, again, an open source module for this. This is the SPI module from OpenCores, given it this link, and it has 4 entry read and write buffers. So the peripheral that we access in this lab is the analog device's accelerometer, and here's the data sheet for that. And so this shows the accelerometer here as a peripheral, and this is the RVfpga system as the controller in green on the left. So again, just showing the same figure, that the format is very similar for each of the peripherals, right? We have the interface with the processor on the right, the hardware to interface the accelerometer, and then the actual physical interface with the wires to the accelerometer on the left of that figure. In labs 11 through 20, again, we're switching now to talking about the processor core itself and the memory system. So lab 11 focuses on how do I configure this for VH1. We give a configuration in the RVfpga system, but we show where to make that configuration, how it's organized, and also we talk about performance monitoring. So here's a figure from Western Digital of the Swerve EH1 pipeline. So Swerve EH1 is a 32-bit two-way superscalar 9-stage pipeline in-order processor. And it has these 9 stages numbered 1 through 9 here on the left of this figure. 2 fetch stages, align and decode, and then 3 execute stages followed by commit and write back. And you can see it has 2 integer pipelines, I0 and I1. Those are the 2 ways of the superscalar processor. And then it also has 2 pipelines, load store pipeline and a multiply pipeline. And those are pipelined. And then it has an out of pipeline divider unit. And here is the organization of the source modules, so the Verilog and System Verilog modules. And again, these are all included in the RVfpga package. So it has the Swerve module, which is the CPU, and the memory module, which gives the memory units and the memory hierarchy. We have an instruction and data closely coupled memory. So ICCM and DCCM, those are on-chip memories. They are low latency memory, so we can access them in 1 clock cycle, and the instruction cache. So here's an example program that shows a multiply and an add. And so it's just kind of repeating this loop so that we can view how these pass through the pipeline. And so the first thing we look at, and this is these are all figures from a Verilator simulation, so the Verilator HDL simulator. And so we first see the fetch FC1 and FC2, the two fetch stages of the core in the cycle 1, the leftmost cycle, and the cycle 2, followed by an align stage. And in the align stage, we can see the two instructions being fetched. So those show the machine code for the multiply and the add. And so this is similar to what we saw in the demo, where we could view the two ways of the processor and the instructions being executed in those ways. And this describes in text what I just said. One thing I want to point out is that the fetch unit, the fetch stage, FC2, fetches the instruction. It's actually fetching 4 instructions at once. So this left side shows 2 instructions, and then these instructions that we were interested in were these 2 on the bottom, the multiply and the add. And so it actually fetches new instructions every other cycle because it fetches 4 instructions at once. And then followed by the align stage to extract those multiply and add instructions into way 0 and way 1. And this is, this text is very small, and in the labs you can zoom into it. But the main point of this is to show that you can see the signals, pull them out from the hierarchy of the RVfpga system modules in Verilator, as we showed in the demonstration. You can kind of dig down into that hierarchy and pull out which signals you want to look at. And then we can see the instructions traverse through each of the stages. Here we've highlighted the decode, the execute, the 3 execute stages, and then commit and write back. And this describes in text what we just looked at in the waveform. So lab 16, we start talking about hazards, and particularly this actually had a few data and structural hazards in the previous labs before this, and this one we talk about control hazards, particularly those caused by branch instructions. So control hazards happen when we, as in a branch instruction, we don't know the address of the instruction that we're going to fetch next. So a branch needs to calculate that and see if it's going to be fetched at all, if the branch is taken or not. And so control hazards may stall the pipeline or predict whether the branch is taken and start fetching instructions from the predicted path. And then if the prediction was wrong, it'll flush those instructions out of the pipeline. So we show 2 possible branch predictors. The first one is a naive branch predictor that always predicts the branch is not taken. And we show using the performance hardware that in fact the performance is not great, but the hardware overhead is nothing, right? There's no extra hardware that we need for that. The second branch predictor is a G-share branch predictor, which offers high performance, but at the cost of extra hardware. So we show that trade-off between hardware, added hardware, and performance as well. And so this lab analyzes the execution of the branch equal instruction using both types of branch predictors. In lab 18, now we start to show how to add new features to the RVfpga system, particularly instructions and counters. So we show how to add the bit manipulation instructions from the bit manipulation extension in risc-v, so the B extension, and also how to add floating point instructions. So the SWR VH1 core does not support floating point in hardware, and so we show how to add that functionality, and we also show how to add a hardware counter. In this case, to count the number of I-type instructions that are executed. This last lab that we're going to talk about, lab 20, talks about the memory hierarchy and benchmarking. So the ICCM and the DCCM, the closely coupled memories, the data and instruction closely coupled memories. So these scratchpad memories, the ICCM and DCCM, are on chip and they're low latency. And so we show, especially using benchmarking, we show the difference in performance using these closely coupled memories versus the off-chip memory. And so here's a figure showing the memory map or the address space for instructions. And so we have the SWORD-VH1. It can access the ICCM, the on-chip memory. We called it 3 different things now: the ICCM, the on-chip memory, and the scratchpad memory for instructions. It's shown here on the bottom. And it maps to these addresses in the memory map. And again, that delay for accessing that is 1 cycle. Or we can access the off-chip memory, which is the DDR external memory. It takes 22 cycles to access that memory unless those addresses are cached in the instruction cache. We also have a space for data memory, and we have external memory, again, our 22 cycles, or the DCCM, the on-chip memory, which is, again, 1 cycle mapped to these addresses shown at the bottom. And so we show how to run benchmarks, especially to explore memory hierarchy and different configurations and what the performance benefits or costs are. And so benchmarks run a set of programs on a processor, and they're useful for us to compare processors. So we run the same benchmark across different processors or different processor configurations, and then can compare them. So 2 common benchmarks are CoreMark and Drystone, and these 2 benchmarks have published values for various processors. So we can see what we can evaluate what our architectural changes, what the effect of those are on performance, and compare them to other processors. So benchmarks use hardware counters to measure events such as number of instructions and number of cycles. And so here's a list of the special purpose registers used to record performance and other metrics from the SWORD-VH1 Programmer's Reference Manual. And we'll show an example of some of these. This is just to show that there is a detailed list of all of them. So the way that we use and initialize hardware counters, again, we provide code for all of this, is we include the platform support package from Western Digital, and then we enable counters. So there's an API for enabling counters. And then we set counters to measure various metrics. So for example, if we want to set a counter for the cycles that the clock is active, the number of instructions that are committed, we do that as shown there. And then we can read those metrics. So we can say, well, the cycle end is ESP performance counter get. We get that counter that we've named in the prior lines of code. And then finally, we can print those using the print function, printf nexus, that we talked about earlier. And so here's an example, some actual code showing those, where we have the instructions at the beginning, instructions at the end, how many, right, there are lots of instructions. Usually we have some setup, preamble to the actual code that we want to know the performance of. So we figure out what that number is at the beginning of the code snippet of interest, and then at the end to get the difference between those. And so first we assign the counters, as we showed in those 2 lines before. We enable the counters, of course, first, and then we're going to read the counters at the beginning of the code. So cycles beginning, instructions beginning, and then we read them. We run the code of interest. This could be the benchmark or some other piece of code that you want to run. And then we read those counters again at the end of the code, subtract them to get the difference, right? The total cycles during the time that we have interest, which is running this code, and then the number of instructions during that code of interest. And so we talked about, so CoreMark. CoreMark is one of kind of a standard benchmarking suite of programs. CoreMark metrics run multiple iterations of a loop. And so we have different metrics here. The CoreMark score is the number of iterations it completes per second. Sometimes we refer to this as iterations per second, but it's the CoreMark score, or CM. And then we have CoreMarks per megahertz, which divides this CoreMark score by the clock frequency in megahertz. This is called iterations per second per megahertz as well, but also called CoreMarks per megahertz. And so remember the ideal IPC, instructions per cycle, is 2 for VH1 because it's two-way superscalar. So ideally, we're running 2 instructions every single cycle of the processor running. So here shows the CoreMark performance under various configurations and optimizations. So we have our CoreMark per megahertz here on the top line, the number of instructions that we counted using the hardware counter, and the number of cycles. And then we have our instructions per cycle here, the number of data bus transactions, so to the external memory, and then the number of instruction bus transactions. And so the first one, this leftmost configuration, is basically no optimization, right? We're using external memory, compiler is in debug mode, and we can see that we get a CoreMark per megahertz that's really low, 0.47. And we can also view what the IPC, or instructions per cycle, is, and we get 0.25. So that's pretty poor performance, but it gives us something to compare against, right? This is kind of really not great configuration, lots of instructions, and then we can start putting in our optimizations. So this second one, the second column, shows when we're still in debug mode on the compiler, but now we're using the data closely coupled memory, so the DCCM, that on-chip data memory. And so we look at this and we can see, okay, well, our performance went up. CoreMark per megahertz went up to 1.88, and we still have the same number of instructions because the compiler mode is still the same, but now the number of cycles has dropped dramatically. And so we have a CPI of about 1. I mean, well, turns out to be the same here, but instructions per cycle of 1, and we have 0 data bus transactions. So now all of the data accesses hit in the DCCM instead of having to go to external memory. And so all of these have an instruction cache, so the instruction bus transactions are low. The last column, the rightmost column here, shows the compiler as optimized. So we have an optimized flag, and then we're still using the DCCM. And now we can see that because we've optimized the code, we have a lot fewer instructions, so 0.3 million instructions instead of about 0.5 million. And now we have a higher CoreMark per megahertz, 3.47, and we can see, not expected to change for the instruction bus transactions, and then everything's still hitting within the DCCM, the on-chip memory. So benchmarking is a useful way to, again, evaluate the changes that we make architecturally. And CoreMark is a common one, and you can look at published values for these. And this is a sampler, right? So we can make other optimizations, additional compiler optimizations, and and so forth. And so we show how to run those steps to get users started with that process. So I want to talk about a few of the future developments. As I mentioned earlier, we're going to develop an edX course. We're working on that right now. And we'll also extend RVfpga to the Swerve EL2. So this is a smaller processor, a smaller core than EH1, and it has a simpler pipeline. So it has a 4-stage pipeline, similar to the one that is found in the Digital Design and Computer Architecture textbook that I talked about earlier. It's a single issue, so not dual issue, but it implements the same architecture, RV32 IMC, so 32i with the multiply, divide, and compressed instructions extension. Another development that we'll do in the near future is to target smaller FPGA boards. And an advantage to this is, well, they're smaller, they cost less, and so might be more affordable for courses in universities or at different companies. And so two boards that we're going to target are the Basis 3 and RDA7, and we'll show how to do this process. So some people may ask, well, I don't have any of those boards. Well, we'll show that process, and if you happen to have a different board, you can follow a similar process to target it to a different board. We will also be running RVfpga workshops in the US, in Europe, and in Asia. And for example, one that is currently scheduled is at High Peak on June 22nd of this year. So I want to remind everybody where the download link is if you haven't gotten that yet. It's from Imagination Technologies University Program, again, led by Robert Owen. And so if you haven't done so already, click on that link and register and then receive that package that includes everything that we've talked about today, except VidBo, which is in the beta version, which will come out later. But after completing this course, you'll walk away with this commercial core and SoC and the ecosystem for using it, and then understand how to both explore and understand it and modify it. And so I'd like to thank everybody, especially Digi-Key for hosting this webinar, and also all of my co-authors, especially Danny Chavert from the University of Complutense, Madrid, and all of the other industry and academic sponsors and collaborators. It's really a wonderful collaboration, I think very much in the spirit of risc-v, of being able to build this entire system. So with that, I'd like to thank everybody for being here and open it up for any questions. And I see that as I've been talking, there've been a bunch of questions as well. So that's wonderful. Thank you.
Thank you so much, Professor Harris. And so there is a question on, can you give an estimate of the number of LUTs needed for swerve?
So on the Nexus A7 FPGA board, it uses about 50% of the FPGA. So the number of exact LUTs, I don't remember, but you could view that. Was there another question?
There's a lot of questions. We have some people asking about your new book and how it relates to this, how you go between them, and.
Well, how to go between them is lots of late nights and early mornings. But so the textbook, the Digital Design and Computer Architecture textbook, the risc-v edition, is kind of a precursor for this course. So understanding that material that we go over in that textbook really helps in being able to use this material in the RVfpga course. So that's one nice thing about the RVfpga course is we also do review a little bit of that, but having that foundational knowledge of digital design and computer architecture really helps a lot.
Perfect. So we're getting a lot of questions on porting this core to different FPGAs and different boards. The range of devices range from Zinc to a slightly different flavor of the Nexus A7, or maybe even the Basis 3, which has a much smaller device. So do you have any feedback or comments on the portability and the ability to implement this on a different FPGA?
Yeah, that's a great question. So one thing that we're the feature or developments that we're working on is to target it to different boards, so including the Basis 3 and RDA7. And so also one wonderful thing about RVfpga, it is a community, and so there's a community forum on Imagination Technologies, and if you take this and target it to a different board, we'd love to hear about it as well. So we will be showing how to target different boards in a future release of RVfpga. And then, there are many other labs and, target boards that people can use, and would love to hear back after you've used it, and, you want to target it to a different board. Would love to hear back from you about what you've done with it.
Thank you. And then we have some people wonder about when your next edX course will be published, or what the roadmap is down the road.
Yeah, so we're aiming for this summer. I never like giving an exact date until it's actually done, but we're certainly working on the edX course now, and hoping to get that out sometime this summer. And now I've said it, so it has to be done.
And then there's always the question about, what would it take to extend this to Linux? Because everyone wants to run Linux on a little FPGA that's low cost.
Yeah, so we do show how we do show how to run the Zephyr RTOS using in the SoC course. So certainly, you could follow some of those steps, and would love to see it. So if you follow that through and do that, we'd love to see that, and certainly even point everyone to that.
As a follow-up question to the resources that are used by the core, so does the LUT count include everything, including the DDR controller?
Yeah, so that 50% of the Nexus on the Nexus A7 FPGA, that includes everything, including the DDR controller. So I see a question about whether the Nexus A7 50T can be used. You'd think so. When I said 50%, it's the 50T is a little bit too small for this version, but so the Nexus A7 50T board cannot be used with this. But again, we're going to target in the future. We're targeting the EL2, which is that smaller core, and will fit on smaller FPGAs. So we're going to show how to do that in a future release. And someone asked if 200T could be used. Yeah, certainly 200T could be used. We haven't done that, so but it would be big enough to include the RVfpga system.
Professor Harris, is there a place where people can share their various implementations of RVfpga on boards that are not the Nexus A7 and also not the Arctic 7 device?
Yeah, that's a great question. So we would love to do that, and I think the way to go about that is to post on the RVfpga community forum, which is available on the Imagination University program website. So there's a forum for RVfpga, and to post and say, hey, I've targeted this, and we'll see that, and we'd love to check that out, and then point other people to it as well. And that is a public forum, so other people will be able to see that as well. Yeah, that'd be wonderful. We'd love to see that.
And there's always a lot of questions about registering. There are two developers at ImageTech that are approving it, so after you register, just give them time. So they will approve it, but it's not automatic. It's fully manual.
There's a question about the version of Vivado that's being used. In this course, it's very specific to Vivado version 2019.2. Could earlier versions of Vivado implement this as well? And also, why not 2019.3 if there's 3 or 4, or even the 2020 versions? Any comment on that?
Yeah, so great question about versions of Vivado. So here's always the hard thing is we can't test all of those versions, and so it may work on later ones. I think we ran into some problems with 2020 version, but we can't test it on all of them. We know it works on 2019.2, and so that's why we listed that. But that said, it could run on different versions as well. So we list 2019.2 for Vivado because that's what we've run and tested it on extensively.
Another question is the core open enough as a design to implement on something other than a Xilinx device, or would this be entirely up to the individual user?
So whether they could use like an Altera device or some other FPGA, is that what you mean?
Yeah.
Yeah, certainly. So people can certainly use this and then target it to a different platform. That's fine. The RVfpga system itself has been funded by Imagination Technology University program. The core, the SOAR VH1 core is fully open source, and so is the SoC, the Swerve-Ulf SoC provided by Chips Alliance. So the materials, it's not, it's certainly not free for Imagination to develop these materials. And so if someone took them and said that, oh, they're our own, please acknowledge Imagination Technologies. But certainly would love to see as many people use it as possible. And I think I saw a question about whether the slides are going to be provided. Yes, they will be provided as well by Digi-Key.
And Robert Owens wants to talk about that. You could just ask in their forums too about other architectures. So while they're mainly doing Xilinx stuff, that's where a lot of the community talks about doing other architectures. So
yeah, we'd love to see that.
I think as somewhat of an affiliated question here, is there support for VHDL? So,
just like any RTL project, you can have VHDL modules. We don't supply, the RVfpga system is not in both, System Verilog, and VHDL. But if you want to add modules, you can certainly add your modules in VHDL. That's not a problem. So there was a question about if there's a GitHub for RVfpga. So RVfpga is actually distributed via the Imagination Technology University program. So it's built on open source core and SoC. The materials are available through Imagination though, so that you need to click on that link, and then they're free, but have to register. There's they have supported the development of this both financially, time-wise, and so they mostly want to keep track and see, hey, what are people doing with this? They want to kind of keep in touch with people who are using the system.
Another question here about implementing RVfpga into an FPGA coursework. How do you envision this fitting into an FPGA curriculum? Can this be taught at the very early stages of working with FPGAs, or should this be saved for a much more advanced class, or can this be an extracurricular activity?
Yeah, that's a great question. So ways that we've used this material in in our own courses here at UNLV and in Madrid and in other places that we've been working with, typically as a follow-on course to the digital design course and computer architecture course, and then this would be the third course. So those are typically second or third year courses. So this would likely be a third or fourth year course for labs 1 through 10. And then the labs 11 through 20 are really upper divisions of fourth year or even or master's level courses. So, that's typically where we would integrate it. Really understanding digital design and computer architecture is a must for this.
And this is coming from some users. If I was a university and I wanted to teach this course, what would I have to do?
Download the package and start using it. Yeah. So if you're a university and want to use it, if you're an industry and want to teach your colleagues about risc-v and FPGAs, download register for the download it, and then you can get started using it.
So are licenses provided for teaching the RVfpga material in a university course? Or in other words, are all the licenses needed for instruction included as part of the package?
Yeah, this is a great question. Yeah, so as long as you've registered at Imagination Technologies and been approved for the download, you're welcome to use it in your courses. There's no additional licensing beyond that. Of course, we would love to hear how it goes and would love to hear your feedback. But as far as licensing or approval, the registration process is that. That's all you need.
Okay, here's an interesting question. So, would you know if the synthesis tool from Vivado infers DSP48 for the core so as to save on the LUT resources? Or is that something that is being done or tested?
Asking about the LUT resources?
Mm-hmm.
What do you mean, have we tested it?
Have the core being implemented with inference to DSP48 as opposed to LUTs in the...
Okay, no, that's
FPGA.
not something we've done. Yeah, that's not something we've done. It's interesting, yeah. Would love for you to do it. Tell us how it goes. Yeah, we have not done that. Yeah, good question.
Another question is it possible? Oh, please go ahead.
I was going to say, there's been a few people asking, why RFPGA? What's the history of it? Why animation? And so maybe the background would help some of these users because it's an interesting story.
Yeah, I almost want to turn it over to Robert Owen if he's here to give the history, but I'm glad to do it too. So if Robert's here, feel free to jump in. But so that's a great question, Robert Nelson. So we started with the MIPS FPGA program back in 2015, where we were targeting a MIPS core to an FPGA. And risc-v, I think as we all know who are here, is the first really kind of adopted open source architecture. And so it offers a great opportunity for innovation. And so because it's open source, there aren't, someone asked a question about licenses earlier. There aren't those hurdles, and often that takes, months and months and lots of negotiation. And so risc-v being open source really opens up a lot of doors for innovation. And Imagination Technologies is, number one, they want to drive innovation, and they use risc-v cores in their own products. And so being able to, to get people quickly, right? You saw in the demo, the 7 to 8 minute demo, can quickly access these materials and use them. After you've gotten a download, you can go from downloading, install the software may take some time, but then after the software is installed, to using it within minutes, 20 minutes, you can start running stuff, running programs on the risc-v system. And so that's one of the motivations, is to be able to help people get into that space and understand how to use the tools and understand the core itself. So Imagination, is a proponent of risc-v and uses risc-v cores themselves. And, this Robert Owen has been a great proponent of innovation and education about cores, especially risc-v. Can you explain the architecture of risc-v core? Yes. Get my book. Yeah, that's the short answer to that. Yeah. Right. Any other questions? Can I show my book? I would if I had it here. That would have been a good idea.
I'll help you out, Sarah.
Yeah, there you go.
There you go. Yeah, we should probably put a link in there for Amazon how to get it. So,
thanks, Robert. I think we have time for one or two more questions. If you want to pick one out. So there's a question about how to register for the June 22nd workshop. So it's part of the High Peak conference. And so you would be part of that conference, register for that conference. We will also be having some workshops in the US as well, which are free. So we'll be publishing those and posting information about those. One nice thing about when you register too is then you'll receive, as we have updates, you'll receive these updates of, hey, we're having a workshop, here are the dates, here's how to register. As you do that with Imagination Technologies, as you register, you'll be able to get those updates as well. So we're planning some, probably the end of, in May, starting in May in the US as well.
I see we have the interesting question about ARM coming up here too. So your thoughts on Sarah on what happened with ARM and the future risc-v maybe going forward? So.
Oh, the future of those two architectures?
Yep. As far as like a competition or how one spurns the other to move forward.
Yeah, well, it's certainly interesting. They're kind of like juxtaposed on philosophies, right? ARM and risc-v. And I think, I think the open source nature of risc-v gives it a real advantage over other architectures. So, we'll see where that goes, but I think that open source nature really, probably gives it an edge on that. There was a question about when we estimate that the VidBo simulation will be available. So that will certainly be available once the edX course is available. So we're aiming for this summer sometime. Yeah, and so it's a really awesome feature that you can basically run the board without having to buy the board using the virtual simulation, the virtual development board or VidBo simulation. So
here's an interesting question that goes a little bit into the technical detail of things. I'm going to read it out. So how modular is the branch predictor? How easy is it to drop in experimental predictors? Okay, that's a great question. I actually I might turn it over to Danny Chavert, who's is an expert on branch predictors, but we show how to do that in that lab on hazards, and so it's not that difficult, and you can just follow the steps in that lab that I talked about on branch prediction and on control hazards. So it's not very difficult. Okay, perfect. So I think we can have probably one more question, and then we'll have to bring this webinar to a close today. So someone asked, okay, last question here, and this is probably a higher level learning process question. What is the ideal step-by-step process for learning, I guess, risc-v and FPGAs?
Well, so we present it in our book as in the first few chapters, you can actually get into FPGA programming. And so understanding how to build digital designs using an FPGA is pretty readily accessible after learning about basic logic, logic gates and how logic functions work. And so that's, really accessible within a few weeks of learning that. And so that's the first step is first, what is an FPGA? How do I use it? And then learning about digital design. On top of that, testing your designs in an FPGA is the next step, learning more complex digital designs, and then computer architecture, and then targeting your processor to an FPGA and running it on an FPGA. So I think those are the logical steps that we also follow in our textbook.
Okay, perfect. So I believe our time is almost up, and there are a lot more questions that I see in the list. We will take these questions offline and answer them in the order they're received over the next few days. In addition to that, the webinar will be recorded, and it will be available after today. We will send the link out to the participants and all those who have registered for the webinar. So finally, I'd like to thank Professor Harris and also everyone who is in the support team with the Q&A questions, and also thank you very much to our attendees who actually took their time off. I see people from around the world, so I understand it may be late at night for some parts of the planet, so I really appreciate you all coming on today. And stay tuned for more exciting webinars from Digi-Key, and we may very well come up with a part 2 to RVfpga and maybe an encore for Professor Harris or some other parts of imagination technology as well. So thank you very much, Professor Harris, for joining us today, and also to our audience members.
Thank you. Thank you, YC. Thank you, everyone.
You.